Okay, thank you, Vanya. Thanks, Chris, and the whole team for giving me this opportunity to talk about some of the work that we have been doing for the last 8 to 10 years now. I think the theme itself.
Sorry, yes. Anand, may I interrupt you? We could see, but now we can't see your. Yeah, now we can. Thank you.
So our work for the last 8 to 10 years that we have been doing, I think the theme has been perfectly set by, Vanya has been talking about the circularities, the sustainability. Chris touched upon a very important aspect of various metals, which are not that much earth abundant, but they are very important in a variety of processes, and we are slowly losing them. So that is one of the themes which I am going to talk about as well. He also talked about phosphorus, and I have some amount of phosphorus work also going on in our chemistry. But to tell you, the science which we do is mainly related to the work. We collaborate a lot with companies because the institute what I'm working with in the Institute of Chemical Technology, that's one of the premier institutes in India who are, they interact quite a bit with companies. We do get a lot of questions from the companies on sustainability, circularity, coming out with better processes, trying to work with metals which are more sustainable or more available. So that is kind of the science which we do, and this is something which I'm going to discuss today. Now, phosphorus, I think we kind of know that most of us have been exposed to phosphorus chemistry sometime during our undergraduate, master's, or PhD. And we do know that phosphorus in common places has the lone pair. They are sigma donors, very important molecules. They are used consistently in reactions, processes, catalysis as ligands, and they coordinate very strongly with metals, making the metals more electron rich. That enables the metal to have properties which can have coordination properties. It can insert into a variety of different bonds. And in such a case, the ligands which have been shown in front of you, they have been one of the most important ligands which have been used in academia as well as industry. You also have slightly constrained type of phosphorus ligands where all the three coordination sites have been constrained into a formation of a cage. These are called as the cage phosphines. These are also very effective ligands, sigma donors to a large extent, but they provide another aspect which is more sterics. Now, overall, if you see the structure of all these compounds, there's one thing which does have a problem, that these are majorly organic or sometimes even aromatic in nature. So from a circularity or the sustainability point of view, many times if you have more rigid structures which are not easy to biodegrade, then in the over a period of time, when it comes to commercial processes, it could be a problem. But we are going to talk about certain reactions which we have been working with, and these are generally the cross-coupling reactions that have found a lot of application in companies even now. When it comes to aromatic halide, the CX bond activation, that has definitely been very useful. But in case of heteroaromatic halides, there has been lacunae which have been seen in academia as well as industry. And important point here is the precious metals such as palladium, rhodium, ruthenium, nickel, they have been used extensively. While if you have seen what one of the photographs what Chris showed, where the metals which are in the red or orange region, they are not earth abundant and they are also very expensive. So we have to be very careful on how we use these metals. But switching from one metal to another is not so easy, and that is something which takes a lot of time. However, there has to be a push, there has to be a thinking that we need to go in that direction to develop better sustainable processes. So this is a journey what we have done in the last 10 years or so, when we have interacted quite a bit with the companies. This is the ligand which we have been working with. This is what is called as triazophosphoadamantane. It's a very simple structure. It is very compatible. The one thing which is very important, this molecule degrades very rapidly in terms of acids. So you can have the carbons and nitrogens separate out very easily. So overall, the structure has a possibility of biodegradability. But that was not a major point. It has good amount of water solubility. And why water solubility was one of the key factors for our processes was when we were interacting with one of the main companies, Heteroarene Corporation. It's an American company. And we started working on this very important area, which is called as nucleoside modifications. The one problem which industries were having when it comes to replication of this chemistry was most of the ligands what we have seen, they were all aromatic in nature, and in most cases were not water soluble, or they are not, they cannot be easily recycled. So water solubility plays a key factor when it comes to highly, polar molecules and solubilization of the molecules and carrying out various processes. So we decided that we could simply functionalize this PTA into a very easily zwitterionic molecule called as PTA-BS. By a simple reaction, this is called as a sultone, and it opens up to fall from this zwitterionic sulfonate. Naturally, the water solubility of the ligand enhances rapidly, and now you can carry out the reaction extensively only in water as a solvent. Now, the question is why water is more preferable is because the compound which forms at the end of the reaction can be is more hydrophobic, and it can be easily recovered without trying to carry out these problematic processes such as column chromatography, where silica as a waste is produced, a lot of organic solvents which are used. So you're trying to get away from that problems which companies generally try to avoid. So if you inculcate this type of ideology into your research as well, then even the students which are supposed to then demonstrate it to the company exactly what type of reactions to be done and how can it be replicated on the industrial scale is something which will be very useful. So you're able to isolate all these compounds without column simply by filtration and very, very small amount of organic solvent for washing rather than creating a lot of waste. We have demonstrated this to a company, Sapala Organics, which is a subsidiary of Heteroarene Corporation, and we did it for a very important reaction, PET reaction. This molecule is a very important commercial building block, and what we were able to achieve is the whole reaction was carried out in acetonitrile water with minimal amount of organic solvent. But the reaction after the product formation, it is the isolation procedure is with least amount of organic solvent and completely column-free. What you're getting is highly pure product formation. The purity of the product is generally 98% plus. And this has been now developed. This has been directly taken up by the company. We showed the process to be working very well at 10 gram in the laboratory, 100 gram on the commercial in the company. And now this has been prepared on kilogram scale commercially. So that provided us with a lot of confidence. But if you look at the catalyst which has been used, it is all metals which are precious, such as palladium. And it does give us confidence that, yes, the reactions are working very well. So the question comes that why is it that this ligand is playing only the role of being water soluble and it is giving the reaction, allowing the reaction to work in water? And is that the only reason that we are working with it? That is not the case. We tried to do some more studies, and the main idea was rather than having the sigma donor ligand or sigma donor properties on the ligand, we are trying to create more of a pi acceptor phosphorus by creating this quaternary ammonium center. And what it does is it chelates very strongly with the metal, which means that the metal, which is precious metal, even if it is palladium, when it strongly chelates with the complex, it is water soluble. We had the chance even to recycle this solution for a period of around 4 to 5 recycles. And the idea was to probably go beyond 10 or 20, because this will be very useful from the company point of view. So what it does is, because of the pi acceptor property of the phosphorus, metal is coordinated very strongly and it doesn't leach out into the organic phase where your product is highly, it is highly pure and you don't have any metal contaminants, which generally are detrimental for the purification. So extra purification is generally required for removal of these transition metals. We also done some more studies to confirm the pi acceptor properties. And we also saw that the size of the ligand, although we have this, the chain length, which is there around 4 carbon atom and the sulfonate, we saw that the size of the ligand was still not very big. The cone angle which it was making with the metal was nothing more than 120 degrees, which was very interesting. And what we saw was slightly when the modeling was done, we understood that probably the sulfonates are playing a very important role in coordination, and they might be chelating to the quaternary ammonium or the other part, or it might also be coordinating weakly electrostatic attraction towards the metal as well. However, these are models, and this is something which we would verify further. But then the question was, can we try to do the reaction, can we carry out reaction for some more important reaction rather than going for nucleosides? So we then entered into a more useful area or more general area of heteroarene chemistry. And what we saw was there are a variety of drug molecules which have been available where CO bond formation is required. And aromatic CO bond formation has been extensively studied, most of the time at 120 degrees or 140 degrees. But in case of chloroheteroarene, the reactions have been a bit on the lower side, where 60 degrees or 115 degrees was something which was achieved. And our idea was whether we can try to minimize the temperature, because there are many times labile, temperature labile groups, which can degrade over a period of time when the reactions are happening at 60 degrees or higher. So our first idea was to try to see whether we can do the reaction in water, although it does work in water, but then we went for an organic solvent like a DMF, and we still get very good yields. But then we came on to a much more bigger problem as amination. That is kind of the theme of my presentation, because this area has been growing rapidly. There is a lot of work which has been done by groups like Buchwald in America, as well as several in Europe, as well as now in China. And idea was whether we can develop a very straightforward synthetic route with a very, very efficient catalyst, which takes care of some of the problems associated with this process. So amination till now had been done in aromatic, for aromatic chlorides, aryl chlorides, or chloroarenes at room temperature, but chloroheteroarenes with such type of pyrimidine or other structures were above 60 degrees or 80 degrees. And our idea was whether we can achieve a room temperature protocol, which is very easy, straightforward. And rather than having the reaction times going up to 24 hours or more, can we reduce them to maximum 4 to 6 hours? And we were finally able to achieve that the reaction proceeds very effectively, although still there is, in this case, we still have to have DMF as the organic solvent and palladium as the metal of choice. The reaction proceeds effectively at room temperature only in 4 hours. Now we can have a derivatized variety of substrates, but that was not really the point. The question was, we are slightly away from the vision of what we had set ourselves. And naturally, there was always going to be a company intervention, which will also help us to understand whether we can make a switch from this metal, which is palladium, which is so expensive as well as not easily available, into something which is cheaper, which is probably 3D transition metal, something which is easily available. So we went ahead, we did some more studies as well. Thioetherification, again, is a major problem. Thiols are generally poisons for a variety of metal catalytic reactions. But in our case, because of the pi acceptor property of the ligand, the nature, we are able to get very high yields as compared to what has been reported in literature. But then that intervention finally came, and we were working with a company, Ather Industries in India. And there is a unique program in ICT where we allow company personnel who are process chemists who can do PhD under the professors in our institute. And one of the process chemists from Ather who was working under me, the question which was very simple, that palladium is very expensive, it is not easily available. Can it be replaced by something much cheaper, much more readily available, and probably more sustainable? So copper was probably our choice. Otherwise, nickel is something which is electronically similar to palladium. However, the question was, it's very easy to write down all these things on paper, but to get to have a process which kind of replaces palladium is not that easy. Here we wanted to also set one benchmark, that if the reactions were proceeding with palladium more in solvents like DMF, can we switch to a benign solvent like water and also make this process so effective that rather than having these column-based protocols for isolation, we can again go for complete isolation without column. One thing which was very important was we had a process chemist who was very well versed with respect to the isolation procedures. And we were able to get a protocol finally where we are able to get, react copper salts with PTAB as the ligand in water at room temperature. And the reactions, all of these examples, which are there, 50 odd examples which the student was able to do, all of these were isolated without column, and we did a scale up of the reaction. We are also able to achieve up till 12 recycles of the copper complex, which suggests that we can even go, and you can see that reactivity is not reducing at all, which suggests that we can use this catalytic reaction moreover for a longer period of time. Now, this can be used as a very effective reaction for even functionalization of drug molecules in late stage modification. This is something which is now a priority with respect to DNA modification or RNA modification or even peptides. So something we were very excited about, that we could take this catalytic process further. And after a lot of extensive work, we felt that copper could be the best alternative to palladium. But these are early days that we are talking about. And that's why we further went ahead to understand the system. We got to confirm it that, yes, PTABS is definitely a bioacceptor, where we tried to react it with selenium powder, and we got the phosphorus enema, and we confirmed that, yes, it is definitely a bioacceptor. But then again, we carry out certain ESR studies to confirm that the copper which is present in the solution is not following the regular path of what cross-coupling reactions were doing. So copper oxidation state was not changing. Now, this was very interesting, that through the chemistry what we were doing of replacing palladium with copper, we are trying to see a slightly different methodology, slightly different mechanism that was coming out. Whether that could be explored further, and this is just a slide which gives you an idea of what is known in literature. So Goldberg reaction, which is a perfect copper CH bond activation reaction followed by amination, has been known since 1904. And the Buckwald-Hartwig combination has been known since 1994, where palladium has been used for similar type of reaction where oxidative addition and reductive elimination steps are known. However, in our case, as the copper oxidation state is not varying or is not changing, we felt that there is a slightly different mechanism where SNAR type of processes are being promoted by this type of copper chelation to the heteroatoms. Now, base catalyzed SNARs are known, or on its own, SNAR at higher temperatures above 100 degrees, 150 degrees are also known. But what we see is, with respect to this catalytic protocol, the reactions proceed in water, it works at room temperature, and it gives you much rapid rates of catalytic activity as compared to what has been known. So this mechanism was something which we proposed previously. We went on to do some more amination reactions. Here, DMF, rather than being used as a solvent, you can generate a very effective starting material such as a dimethylamine in situ, rather than having a gas which is more hazardous on even a company scale. You can activate these with simple bases. You can generate these gases locally, and then you can use this for synthesis of very important drug molecules. You can also prepare deuterated drug molecules as well, and this protocol works effectively at room temperature. Everything, all these reactions again are proceeding in water. It doesn't require any other solvent. Naturally, DMF will play a role as a solvent as well as a reactant, but if you are consuming all of the DMF, then it doesn't generally as a solvent. So water is mainly playing as a role for promoting the reactions as well, along with the complex. We finally again confirmed the complex by doing further studies with ESR. And what we saw is we can extend these reactions into much more complex systems. We can not just have amines, now we can generate thiols, which are in situ locally, only the concentration required for the reaction to happen, and then activate further with an amine, again formed locally for a concentration of whatever is important, and you can convert this substrate into more useful products. very effectively with the catalytic system what we have derived. Now, there have been some more reactions which we have done, which are effective reactions, and it suggests the catalyst does play a role. That is, the mechanism does hold true to a certain extent. And this is mainly the, being proved by the regioselective reaction. So we did some more studies where you can have the CCl bond, two different CCl bonds, and you can have like difference in the reactivity. Although you can see the kilocal difference is hardly 1 kilocal, but still, if you carry out the reaction, it is possible to activate only the fourth position because the coordination of your complex will be in this mode rather than the insertion mode that is generally known to happen in case of catalytic reactions. So what we are able to see is the reaction proceeds almost quantitatively towards the fourth position because you are having coordination, activation of the heteroarene. And then steric factors also play a very important role in allowing the amine or the nucleophile to attack specifically at the position 4. So SNAR is promoted rapidly to go into a direction which generally would give you 50-50% as what can be seen with all the other ligands. We have also demonstrated the same thing because these are very important molecules when you look at chemoselective reactions, when you have a chloride versus bromide or bromide versus iodide, or effectively a fluoride versus iodide as well. In such a case, these molecules are very effective and you can create very important routes rather than the general routes which are having various other precious metals and many times are not that chemoselective. Here as well, you can see one of the example where if you have a fluoride versus bromide or fluoride versus iodide in such a case, the reaction proceeds effectively to work at the fluoride or the position which is next to the heteroatom, while it doesn't try to interact in the general oxidative addition way. So the mechanism does hold true, and there is this bias which is created where more, the less favored CF bond might still get activated over the more favored CI bond. So what we have shown, we have done a lot of other mechanisms, but I'm not going to discuss that today. We see that the ligand does have potential to promote various reactions in combination with metals like palladium or copper. But now we have kind of made a complete switch, and we see that copper is much more accelerated, much more reactive. It is earth abundant. The costing wise, definitely copper wins hands down. But then seems like the ligand role is also very crucial, and we are looking at more further development in this area where we can have more sustainable goal with respect to the ligand structure and the degradation properties of the ligand at the end of the reaction as well, and how we can even allow the recycling to take place further and further, maybe up to 2025. There is one breakthrough which I would like to say, that hydroformylation reaction for synthesis acetic acid which was our focus for quite some time. This has also been achieved. We have got very good results, and the recyclability of this rhodium with respect to the ligand, the PTAPS and ligand is effective in such a way that you can have variety, a large number of recycles. We have just crossed around 5 to 6, and we feel that we can go beyond as well. And that would lead us into another very, very useful commercial process over a period of time. We are also happy to say that this ligand is now being commercialized and with most of the major companies, and it's available for you to buy. You can always collaborate with us and we can always give it to you. There's one aspect of our chemistry which I have not discussed about. This is something which we are also very much interested in, trying to develop highly sustainable rapid synthesis and catalysis processes using continuous flow. We had recently talked about Suzuki-Miura coupling of nucleosides from a commercial point of view, and we have done it using flow technology. Normally, the reaction would have proceeded under normal conditions at around 4 to 6 hours, but this reaction can proceed effectively only in 8 minutes with very high yields and absolutely no byproduct. So highly advantageous with very low cost which is involved, and you can scale it up to gram scale very easily. At the same time, our recent results suggest that we have just published, and this is online now on sustainability and circularity now. And this is a very important molecule, CPC. Commonly, it's like a metric ton scale molecule, and is used in a variety of areas. And we were able to show that you can reduce the time from around 2 days, 48 hours, to only 30 minutes for the whole process to be completed, and very effective. Lot of improvement in the quality of the product and the amount of pyridine, which is one of the main starting materials, and it was always used in excess. We have been able to reduce it quite a lot. So you can do the reaction very effectively using this technology as well. Finally, naturally, my group has been working extensively, but I would definitely acknowledge collaborators and the companies, because there have been a lot of questions which come from the company, and then we interact and we try to come out with better solutions. This program of having company personnel working under us also have developed a sense of understanding in our group that we could try to cater to their problems and we can come out with better solutions. I leave you with this slide. Again, I think Chris has already spoken about this, but if you are interested, please do submit your work to this new journal. And I would like to now thank Chris and the team and everyone for giving me this opportunity. If there are any questions,